Well, good morning. Today we're going to take a look at the law of conservation of energy and use that to solve some problems. So, as you know, the law of conservation of energy says that energy cannot be created nor can it be destroyed, but it can be changed from one form to another. In our example here, we're going to change potential energy into kinetic energy. So, you might recall, quite some time ago, we talked about dropping a bowling ball off of a silo. Here is that same silo. If you recall, it was 72 feet tall. And after the unit conversion, we find out that that is 22 meters. We had done some kinematics using G, acceleration due to gravity, to find how fast the ball was going right before it hit the ground. Let's do the same problem, but using energy considerations. You can see here we have the same silo. Here's the ball of mass M up at the top, and my brother and I, we're just going to let it go. So up here at the top, it has only potential energy. Right before it hits the ground, it has kinetic energy. And the law of conservation of energy says that the potential energy at the top equals the kinetic energy at the bottom. So we just write that equation. We found out the other day that potential energy is mgh, kinetic energy is 1/2 mv squared, and you notice here we have a mass on both sides of the equation that cancels out, and so we're left with this. And if we rearrange the equation, what do we do here? We multiply both sides by 2, take the square root, and then we're going to turn it around. We find out that the velocity at the bottom is the square root of 2gh. If we plug in some values, we find out, same answer we found way back using kinematics, it's going 20.8 meters per second. Now, you might also recall we talked about throwing the ball. Because obviously my brother and I didn't break the bowling ball. We wanted to throw it and see what happens. So instead of dropping it, we're going to give it some velocity. So that's going to be an all new problem. The problem here, if you remember in kinematics, when we give it an initial velocity, we then had to use a quadratic formula in order to solve it, because the initial velocity has a value and that term doesn't go away in our kinematic equation. So we're going to use energy considerations, and hopefully we won't need a quadratic formula to solve this one. The interesting thing about energy, it doesn't really matter what direction we throw the ball. So we're going to throw it at 5 meters per second, and we could throw that up, we could throw it out, we could throw it down. It really doesn't matter. We're giving it kinetic energy if it is moving. Now, we do have to make some distinctions, because now we have kinetic energy both at the top and at the bottom. I'm going to add some subscripts to distinguish those so that we know which is which. We'll substitute in what we know. Of course, potential energy is mgh. Kinetic energy at the top is going to be 1/2 mv squared, but that's at the top. At the bottom, we have 1/2 mv squared also, but at the bottom. Once again, you notice here we have a mass in every single term. So if we divide by m, that cancels out, and we're left with this equation. And of course, we'll do some algebra. We're going to rearrange that. All we need to do is multiply both sides by 2. So I left the 2 here with the gh, and when we multiply this term by 2, the 1/2 goes away, and then of course we take the square root of both sides. If we plug in some numbers, we find out it's going only a little bit faster than we found in the prior example. It's now going 21.4 meters per second.